So this whole concept, listen please, this whole concept is about free falling objects. That's what our whole lesson is today. But what's nice about today's lesson is that there's really nothing new. There's nothing new besides what you just saw in a video a minute ago. Because all the equations we're going to use, all the motion we're going to describe, has already been described right here in these three equations. These three equations are going to be the same three equations that govern vertical motion, just as they govern horizontal motion a little while ago. And then in a chapter or two, after this next test, in the second quarter, we're going to start projectile motion, when it's actually fired in both directions. But right now, we're going to look at vertical motion today. We've really only been looking at horizontal motion when it comes to acceleration in sections 2.4 to 2.6, but now we'll take a look at vertical. The interesting part about vertical motion is that the acceleration is a constant. That's the difference you're going to notice between horizontal. So like if I'm in a car and I hit the gas, I'm accelerating. If I hit the brake, I'm decelerating. I change or control my acceleration based on my movement. But if I were to just drop any object, it cannot control its own acceleration when in a state of what we call free fall. Free fall. A free fall state is an object that's been dropped or it's moving in space only under the influence of gravity. So we're not talking right now about rockets that are accelerating upward. We're going to get to those ideas in this section for sure. But for now, I'm saying just objects that are only under the influence of gravity. If it's a rocket and it propels itself upward, well, it's combating gravity at that point. That's how rockets can escape the Earth. They need a certain escape velocity with which it allows them to actually get out of the gravitational pull of the Earth. So right now, though, we're going to be looking at what if something's just under the influence of gravity, it's dropped, it's tossed upward, and now it's only gravity pulling it back down. So those are the types of problems we're going to look at. What do you think as a variable I'm going to use instead of x? Logically. Y. Vertical motion. Vertical motion. Okay? Now, the textbook also likes to call A, G, for gravitational acceleration. And if you recall, what was that number in your lab, approximately? 10. Around 10. What would you get for more, if you look at your textbook, or if you saw like the number, if you looked it up?
9.8.
Around 9.8. But yeah, in the lab, it was right around 10. Very good. The number itself is actually negative 9.81. Or as a magnitude, just 9.81. So let's take a look at this next slide and see what you guys did in the lab. Here's what you did in the lab. Now, you didn't toss the object upward at first, though, right? You guys just dropped the picket fence. But if you recall, your velocity graph was very much like this, but if you think about the sensors, which way did it show? What direction did it show on your graph when you did it? Yeah, it showed the direction like this, right? Because the sensor doesn't know up or down. So when you talk about a photo gate, it just sees things changing at a certain rate. So when you graphed it in the lab, you all saw this. And again, it was a velocity time graph that you were looking at. And you all pretty much saw something like this. Okay? And that little gap that you saw here was if you had raised it up above the sensor a little bit, it gives it a little initial velocity by letting it go. Because by the time the photo gate reached the picket fence reached the photo gate, it already had some velocity, right? I'm helping you out with the lab right now. So again, when you drop from here, it picks up velocity along the way, so when it hits the photo gate, it suddenly has initial velocity, which is why you had probably a little discrepancy and it wasn't exactly through the origin. Now, in this example shown in the graph up here, what we're seeing is a person tosses an object upward, follow the path please, it reaches the top of its peak, and then what happens? What happens for an instant at the top there? What has to happen, Christina? Yeah, it stops. For how long? For how long? How do we describe that amount of time, right? What would we say?
Like approaching zero.
Very good. As delta t at the top approaches zero. An infinitesimally small amount of time. A very, 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 very small amount of time it pauses for at the top. An amount of time that we can actually consider to not even exist. We could say that it's just a moment that it stops. So how much time does it stop for? And you can just say zero, really. When in reality, it stops for an actual really, really small amount of time. If you've ever watched basketball games and you see somebody dunking, when they're in the air, it actually looks like they almost freeze for a little bit at the top. And there is a way you can make your body look like that, which is interesting. And we'll get to that idea, actually, when you're launching yourself up. But this instance here, we're saying it stops at the top for a moment. So at the top, the velocity is zero. So that's right here. So maybe on this graph, we should label this location as the top of its path, right? That would be good. And then when is the velocity decreasing? Is it going to be decreasing when it's on the way up or on the way down? Or both? What do you think? What about its speed versus velocity? Give me some sort of a statement in your own words about what's going on the way up versus on the way down. Some your own words, go ahead.
Well, if we're using y as the axis, then the speed is going to be positive for going up, but I think the velocity coming down is going to be more even though it'll be negative.
So you're on the right track. You have the right idea that on the way up it's positive, on the way down it is negative. I agree. The more part we'll get into in a little bit more. What else you want to add?
The velocity that actually says positive, and then when it reaches top, it becomes negative, and then it decreases before it gets to the top. The velocity decreases, and then it gets to zero. It stops for a very small amount of time, and then it becomes more and more negative, but the speed ends up increasing.
That's the point I want to talk about right now, because speed and velocity is still something that people are confusing. So let's talk. On the way up, it's losing velocity. It's also losing speed. Right? They're both being lost on the way up. And then at the top, it stops. No speed, no velocity. But on the way down, it's still losing velocity. It's becoming more negative. Remember, velocity matters for your sign. So the sign is becoming more and more and more negative. But the speed is increasing. Because again, what is speed? At an instant, it's the absolute value of the velocity. So if I wanted to graph the speed curve for this, I could technically just do this. That's what the speed would look like. The speed technically can never be negative. Remember we talked about speed. So on the way down, although its velocity is becoming more negative, we would use the phrase, it is speeding up. It is speeding up in the negative direction. It is getting faster in the negative direction. Its velocity is becoming more negative. Its velocity is decreasing. That's the hard part to wrap your mind around. Again, that last statement. So we have 4 statements here we can make, right? Its speed is increasing. The second statement I said. Its velocity is becoming more negative. More negative. But the hard part to wrap around is that the velocity is actually still considered to be decreasing. And that statement comes from the graph. This is a graph of velocity versus time. And the entire time, the velocity is going down. Just literally follow the graph. Now, again, the slope of this, if you recall, we talked about in the last section, the slope, the rise over run for this, is going to give us the acceleration felt. The slope, remember, for a velocity graph is equal to acceleration. And that is approximately 9.81 meters per second squared. That's the number that we're going to use for acceleration, God bless you, for acceleration for free-falling objects. So in all 3 equations where you see an A right now, you can rewrite all 3 if you want. I don't do it. And it's not on your formula sheet. I do not write it with a GN because you got to know. Oh, if it's free fall, acceleration is just gravity. That's all it is. So for all 3, you can put a G in, and for 2, you could replace X with Y. But again, on your formula sheet, you're only going to see everything like this. Yeah.
Just would the number 9.81 be different depending like what place you're on Earth, and obviously like if you're on Mars?
Yeah, absolutely. It's a great question, Jack. And we were going to talk about what causes G to vary. Height on the Earth would cause G to vary. Although we call it a constant, it changes if you're in like Denver, right? If you've been to Denver before for sports, for baseball, or for football, you'll hear about there are more home runs and farther field goals kicked. The elevation helps a lot. There's also thinner air further up. Now, also it changes with respect to the mass of the planet. So the moon's gravity is around 1.6. Jupiter is like 25.9. The more massive the planet, the more gravity it has. We're going to learn about gravity and mass a little bit later.
Does Jupiter have more gravity than Earth? Or?
Yeah, far more. Although it is mainly gaseous, because it has so much gas and it has a core, it has a much higher mass than the Earth does.
Okay.
Yeah.
Is this acceleration 9.81, is that negative or positive?
So in this lesson, Maura, it's a great question. In this lesson, we're going to refer to acceleration as negative 9.81. But g is traditionally given as a constant of 9.81 meters per second squared. It's just given as a magnitude in a lot of textbooks. But in this lesson, because the acceleration is acting downward, when we use the number more, we're going to use it as a negative. But in your lab, if you remember, right, the slope was just positive 9.81 in your lab. Okay, approximately. But in this lesson, we're going to look at it as negative. And more, yeah, based on the look of this line, look what I'm tracing, right? This line here that I'm tracing over, it clearly has a negative slope. And that's why you're asking that question, right? This has got to have a negative slope. So yes, the actual value we're going to use is negative. You can put a negative there if you want. But what I'm saying is that in books, you're going to see it written as just the magnitude, okay? And later in the year, we're going to use positive 9.81 for other applications. And we'll get to when that is, okay? All right, so with that said, let's take a look where we're headed with this idea. So we're going to do 3 examples today. The first one is only 1 part. The second one has 5 parts to it. And then the third one will have 1 part. And what I'm trying to do is teach you guys how you can vary in length of a problem. Although it seems difficult, each step along the way will help you with the next step afterward. Okay, it's a traditional AP type problem will be the second one that we're going to look at today. So the first one is a little bit easier. An object is dropped from the top of the Empire State Building, approximately 443 meters tall. By the way, this is including the spire at the top. Without the spire, it's like 400 or so. And it lands directly below on the ground. Determine the velocity of the object when it makes contact with the ground. How long does it take to reach the ground? Okay, so we're going to write down our givens first, and we'll do this one to start, at least together first. So we see that we're at a building, and if I want to draw a diagram, I can. Here's my diagram. Okay, here's my object, and my object is dropped. So it is useful to draw diagrams. It is nice to see that. It does not have to be to scale. It does not have to look like the Empire State Building. Mine clearly does not. I'll draw cars later this year, and they'll be rectangles, and that's fine. I'll put 2 circles for wheels. So just draw a very simple diagram. Don't waste time on all the artistic work here. So it says first that it is dropped. 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 Tell me, what can I infer from that statement of the word dropped, Isabella?
It's free falling.
It's free falling. It's dropped. What else can I infer from that same statement? Good. I like that it's free falling. Seb.
So the acceleration is negative?
Because it's falling down, we can already infer that acceleration, very good, is negative 9.81 meters per second squared. I like that, Seb. Again, because it's dropped and it's freely falling. Good, both statements. What else?
V0 is 0.
Yeah, V0, the initial velocity, must be 0. And let's talk about that statement, because that's the one that some students seem to forget here. When an object is dropped, it's the instant before it begins to move that this problem begins. So when I hold this eraser here, I say ready, set, go. And you start the stopwatch at the moment I drop it. At the moment I drop it, there is an instant, delta t equals 0. There's an instant where it is not moving for that moment. It's the same exact problem as this. I throw it upward, it gets to the top. What does it do at the top again, we said? It stops. So the V at the top is 0 when it's doing this kind of motion. It's the same concept as dropping. It's as if the object made it to the top and is about to turn around. The turning around point is me dropping it. So whenever you see the word dropped, put a big asterisk next to it. Put V0 equals 0 when you see the word dropped. Yes, guys, either one first. You both have your hands up.
Also, since it's like not in a vacuum, gravity's working on it. Well, gravity would normally work on it, but I guess air resistance as well.
We're going to get to that in 1 second. Hold off for 1 sec, Jack. I like the thought, but give me 1 minute. Maura.
Would, if y0 is 0, would y be negative 443 or positive 443?
So that's for you to infer. That's a great question. You hear what Maura's asking about? He's talking about the position now. So if I call the top of the Empire State Building 0, if I call that 0, which I can, then what's the bottom going to be? Negative 443. But, hold on. Or I can call the top of the building positive 443. And call the ground what?
0.
Do we all see what I'm saying right now? Your 0 reference line is your choice. It's going to continue throughout the entire course this way. When we get to potential and kinetic energy, the same concept applies. So you need to define y equals 0 somewhere. I personally, just so you're aware, I like to call 0 ground level. in all kinematics problems. You could do it either way. But what I'm going to do is I'm going to call this y equals 0. So as a result, I'm going to say that y0 is 443. I don't need units on 0. Has anybody ever been asked that question or understood that? I don't need units on 0. Give me an explanation. Give me an explanation. I'll give you all a little minute to think. Some of you wheels are turning. I don't need units on 0, but I have to put my units over here. George, what do you think?
Well, you're essentially multiplying the units by whatever the number is, so it's just going to be 0 anyway.
Great job, George. That's exactly what you're doing. You're taking the number of 443 and saying, 443 what? You're taking 443 times 1 meter. That's what you're really doing. So 0 times anything is 0. So 0 feet, 0 inches, 0 cubic feet. Now, it is nice to know the units if I'm talking about volume, area, that kind of stuff, right? And I want to say when the volume equals 0 cubic meters because I'm talking about volume. But because of this problem, you don't need units. That's a whole other side still. I was just putting it out there. But you could put meters here if you want to. Okay, but you don't really need units. All right, so I like what we got so far. Let's go back to Jack's question now, because it looks like so far we have most of the information that's given. This is all given to me. We'll get to what's being asked in a minute, but let's answer Jack's question. So his question was this. Well, what if there is air resistance, right? What if the air resistance exists? So what we're going to notice in this course is the following. Unless stated elsewise, you can write this down, there will never be air resistance. The assumption made in AP 1 or honors physics is that air resistance does not affect the problem. It is negligible. Negligible. Now, is that true? That is absolutely not true. Okay? I'm going to make that statement right now because when I was in high school, my teacher told me, oh, air resistance really doesn't matter, it's negligible. That is so not true at all. Okay? Especially when you reach higher speeds. The faster you go, the more air resistance you feel. Do it. Like this. Everybody, do this. Feel anything? Do it slow. I mean, look how slow I'm going. Do it real slow. Feel anything? Of course not. Then do this. You feel, don't slap the person next to you. Sorry. That was a bad thing to do. Sorry. Maybe next time I'll do it this way. But you literally feel the air when you increase your velocity. You don't feel it at slow. You've done it before underwater. Think about swimming. If you're in a pool and you're just walking across the pool, you don't feel the resistance much. Try to run across the pool next time. It's a fluid. Water is a fluid, a liquid. Liquids and gases are both fluids. It's fluidity or fluid resistance. It's called a viscous force. The air you feel opposing your motion is the same as water opposing your hand when you move your hand underwater in the ocean. It's the same thing. It's just that water has more to it, more sustenance or more substance physically than the air around you does. So that resistive force is much greater in a liquid than it is in a gas. But they're both considered fluids. We'll get into that concept later in the year.
Is that why, like, let's say you cannonball into a really deep pool, like sometimes you don't sink all the way to the bottom?
That's exactly what you're doing. Yep. And your buoyancy of the air in your body helps you stay afloat as well. Those two things, really, to be honest. But if you dive in, or if you do like the pencil when you were a kid, you did a pencil, you just drop in, right? You go right down to the bottom. Yeah. There's a cool free fall video I watched on Discovery the other day. It's really long, or else I'd show it right now. But the guy free falls down in this tunnel that they've created of water and holds his breath for 9 minutes to get to the bottom. 9 minutes.
No.
He's a diver, so he goes for a living. 9 minutes. That's incredible to see this. Okay? Yeah, I know. And you know how he does it? If you've ever done this before, we're going to get the points later this year. But if you ever want to sink to the bottom of the pool, just for fun. You let all your air out. Caroline said you blow bubbles out. Your chest, when you let air out, your lungs condense or contract. As a result, your density increases, causing you to be able to sink. Now, in the video, because the guy drops like 400 meters underwater, his lungs compress to 1/5 their size. He lets all his air out first, all of it, and is able to lift all the oxygen that's in his blood only, because there's no oxygen left in his lungs, and they actually physically compress to 1/5 the size. Okay? Don't try this at home. But like a 10-foot pool, try it. Try it sometime.
Wait, how he
Him or he's trained to do it. He almost lost consciousness in the video. They have safety people around and stuff, obviously. So It's not like he's gonna die. People would resuscitate him.
In EMS, they teach you that like more than 6 minutes without breathing is like
More than 6 minutes?
more than like 6 minutes. without-
So this guy, he's a French diver, does it for a living, and trains his body. And he talks. Sorry, not that that makes me. But he talks all about how you have to train your body to get used to it. And your body is used to it. Now, an average person, yes. An average person is probably like 2 or 3 minutes and your brain dead. Yeah, 6 is the number.
6 minutes is like
He's not the average person.
How do they take it out of his blood?
Take what out?
The air.
They don't take air. I said that, sorry. So he takes a deep breath.
Uh-huh.
The air in your lungs gets fed to your blood through your veins,
So it
capillaries.
all came out of it.
And he blows all the air out, so now there's still oxygen carried to the blood. The blood carries oxygen, the heart and the brain. So all that oxygen in the blood is what it's living off of.
Oh, okay.
Yeah, you lose, a lot of that. All right, now, what is the problem asking us for? Determine the velocity of the object when it makes contact with the ground. What variable is that? What variable is, V, right? I heard V right away. Okay, good. And then how long does it take? Thank you, T. Now, if I look at this, I ask myself, I could use different equations because I'm looking for different things. Can somebody suggest an equation to use to find the velocity at the end of this fall, given all the information that we have, which is y, y0, v0, and a. We've got the 4 things in blue. Seb, what are you thinking?
V squared equals initial velocity squared plus 2 times acceleration and delta y.
Very good. Delta y. Good correction, Seb. And it's definitely in the y direction, and this is the equation. How come Seb is totally right? How do we know he's right? How do we know for sure he's right?
Because we don't have T.
Very good. We don't have time. Look at the other formulas. They both involve time. Okay, time is going to be solved for later on in the problem. So let's go ahead and solve this. V equals the square root of that whole thing. Okay? For the sake of time, I'm going to just put the answer. You like that? Yeah. For the sake of time, I'm going to put the answer there. What do we get as a value? What do we get as a number? Anyone calculated already? Yeah, what do you got?
I got 93.23.
Now, when I take a square root, how many answers do I get? 2. Let's put that value now. Which do I choose in this problem? First, make sure Eduardo's answer is right. I agree with him for now. Is it not right? I'm assuming you're right, Eduardo. Yeah, you're right. What answer do I choose for this one?
Negative.
The negative. How come? Who can give rationale?
Because you're
Listen.
moving negatively with the y-axis.
You're moving in the downward direction, so your velocity is the magnitude and the direction. The magnitude is definitely this 93.2 or whatever that value is. And then the negative in front. Okay, so remember, you make the choice. The choice is your intuition you have to use to make that choice. Look at the problem, dissect it, and ask yourself, is the object moving up? Is the object moving to the right? If so, it's positive. If it's moving left or down, the answer must be negative. Second part of the problem, find the time. Now, we have 2 formulas, right? Either can be used. Which is easier to solve for t if either can be used? The top one. Do you see this? The bottom one, to solve for time, becomes a bit annoying because you have to take a square root. Now, v0 is 0, so this drops off. Right? Take a look up. This drops off, and this drops off. So both equations get much simpler. But you still have to take a square root to get time here. So choose the first one for simplicity. But both would work. Both would work. And I show both in my notes. So when you look at my completed notes later, if you're studying, by the way, you have noticed that, I hope, that I put my notes that are completed up online afterward. So all the slides that you're taking notes on right now, if you're missing class or you're out someday, the completed notes are there. Maybe for your test, if you want to read through my notes, I put a lot of tidbits in there that might help you to think a little bit clearer. So here this becomes 0, and I want to figure out time, so it's just V over A. Okay, it's just V over A. That's all it turns out to be again because V0 is 0. There's no initial velocity, it's dropped. So my V value is negative 93.2 divided by negative 9.81. Yep,
I know, oh wait, I have one.
around 9.5. Go ahead.
I know that it's easier to like solve for t first, but you can also just not do that, right? football?
Okay. You could get t first, and you could use this equation over here, right? Because this equation does not involve final velocity. So you can absolutely use the third of the big three and get t to start the problem. Sure. It doesn't matter in this problem, Julia. There are other problems that are going to have A, B, C, D, E. I would recommend on an AP exam, you go in that order, because usually A leads to B, which leads to C. Okay? But yes, you could have done it either direction here.
So obviously the time can't be negative, but what you did is it's negative 93.2 divided by negative 9.
Correct. Yep. The velocity is negative, so is the acceleration, so the time it takes must also be negative. Remember what acceleration is. What is acceleration?
The difference in velocities and
Good definition. What is it physically though? It's how much velocity you gain or lose every second. So think about this, please. Do the math. I need sanity checks. I need people to listen and look up. 9.5 seconds. Every second you're gaining this much, right? If you were to just multiply these two numbers, you would get back to here. Because again, every second along the way, but 9.5 seconds long, you're gaining this much. So take this number and multiply it by here, and that's what you get. And that's right here. The acceleration, which is 9.81 times the time of 9.5 seconds, gives you the speed or velocity at the end. I want you to physically understand in this class, not just be able to regurgitate math. So when you think about an answer at the end, think about its sensibility. I used to call it a sanity check. In high school, actually, my teacher did. It's so funny how much you, like, as a teacher now, you use stuff that your teachers did that were really good. Mr. Dixon called it a sanity check. He said, is your answer sane? Does it make sense? If I have an answer of like 2 million meters per second, it just doesn't make sense. It's not logical as a number. But then I have to also look and say, why did I get a positive answer? Because it's negative over negative here. It makes sense as an answer. Now, I want to ask you this question. Somebody on Google real quick, convert this to miles per hour. 93 point, just type in 93.2 m/s like this, and then write the word 2 mph. That's an easy way to convert on your iPad when you're at home and stuff. You don't want to do the math. What does it come out to be in miles per hour? I'm just curious. 208 or 80? 80.
Yeah.
208 miles per hour. Think about that. So clearly, if we drop something in the Empire State Building and it's falling at that rate, it would kill someone. It would literally kill someone. There's an old adage of something like, if you drop a penny from the Empire State Building, it could like crack someone's skull. It's not true because of air resistance. So the idea is that, if you didn't count for air resistance, it's going to be at 208 miles per hour. It is not going to reach 208 miles per hour. It'll reach what earlier? What do we call that again? Terminal velocity. Good word there. Or good phrase. Terminal velocity. It'll reach that much sooner. Okay, it will not reach that velocity. Let's example 2 here. Example 2 has 5 parts to it, but again, we should go one step at a time. A toy rocket is launched with an initial velocity of exactly, 25 meters per second straight upward. That's important. If it's not straight upward, if it's at an angle, now it's projectile motion. Okay, straight upward. Your book might just say upward. I'm just being more specific here. After how much time will the rocket reach its max height? So don't look at part B, C, D, E yet. Just look at part A. Let's start by listing our givens for part A. What are our givens for this problem? Go ahead.
You know the initial point of y0, v0, and then y will also be 0.
Y0 is 0. I like that. Hold off on the Y piece so far, okay? How about V0? What's V0 in this problem?
25 meters per second.
Okay, we know that Y0 is 0 because we're starting at the ground, but we want to get the time to max height. So for now, I'm only going to go to max height. We're going to come back to the ground later, so you're looking ahead already. So hold off on the Y part for now. So we don't know anything about Y yet. We're not going to be sure about that. But we want to know, after how much time will it reach max height? What other piece of information do I know about max height? At max height, very good, man. The velocity is 0. At max height, which is where we're looking at, the end of our problem, the velocity is 0. So for part A, I want you guys to visualize a diagram like this. Okay? This is what's happening. It starts at the ground and it goes up to the top. And that's the end of part A. That's the end of our problem as far as part A is concerned. What we're doing right now is we're truncating the problem. I've used that word before. I'm breaking the problem into pieces. On the way up will be part one. And then what do you think part two will be? On the way down. And then maybe at the end, what might we do? Maybe we'll look at the whole thing also. But we might look at it in different segments along the way. Start to train your brain to do this. As time elapses, we can call a halfway point, a three-quarter way point. We can break up the problem into pieces. That will really help a lot.
We also know that this acceleration is negative 5.
Very good. And we always know acceleration is negative 9.81 meters per second squared. Okay, and that's vertical. So based on the given information, what formula will I use to figure out how much time after how much time will the rocket take to reach that height? What formula will I use if I'm trying to find time? Eduardo?
V equals V0 plus VT.
Yep. I would agree. Looks like we've got everything there. We're looking for time. So go ahead and solve that, please, algebraically for time. Isabella?
Is the acceleration still negative if you're going up,
It is, because which way is acceleration always pulling you?
like faster, so?
Which way is gravity always pulling
Oh,
you?
down, okay.
So even though your motion is up, that's positive velocity, Isabella. But acceleration is acting negatively, and therefore you are decelerating.
Oh, so we're like, in these types of problems, we're like thinking of A is G, and G is just.
Absolutely right. Very good. Yep. On the way up, you're always decelerating. On the way down, you're accelerating. Again, slowing down on the way up, speeding up on the way down. That's the difference. Speeding up means accelerating. Slowing down means decelerating. That's what those vocab words are. So we want to find time. Let's subtract V0 and let's divide by A. Okay, there's time right there. V minus V0 over A. V minus V0 over A. So it's 0 minus 25 divided by negative 9.81. Okay, again, I could have done this in the beginning. Oops, I'm sorry. I could have done this in the very beginning of the problem. Okay, and I could just call this 0 right here. Because again, it stops at the top. It stops at the top. And you know what? Some textbooks like to do, which is really nice. Some like to make a subscript for T, and they call it T max. What do you think max is really standing for?
Max million.
No, max million, no. Yeah, max height. The time it takes to max height. That might be a useful technique in this course. I've found that some students like to do that so they know when they're doing the problem, what part of the problem they're looking at. They're looking at the time it takes to get the max height. That time will be a value of 2.55 seconds. Check my math always, please. I'm just looking at my numbers I've written down, so always check my math. Let's go to part B. So again, let's help ourselves here. Let's let parts earlier help us for later parts. Let's see if this one does anything. What is the rocket's maximum height? So what variable are we looking at now? What variable if we're trying to find height? We're looking at y. And you know what? You might even call this y max if you want to. You can call it y max, and that's fine. But again, it's the y value at the top. At the top. So now take a look at the equations. Which equation can we use to find y? Well, the first one doesn't have y. Everybody sees that, right? Can we use the second one? Do we have v final, the velocity at the top? Do we have the velocity initially?
Yeah.
We have acceleration, so we could use this to get y. To get y here, do we have the initial y? Sure we do. We have initial velocity, yep. We've got the time it takes, yep. We've got acceleration, so which one are we going to use? What are you thinking? What do you think it said? Which one? The second one?
Yeah.
Why?
Seems simpler than.
It seems simpler because you see a square, right?
But also to get delta y, you need to like.
You know what she's going to say now? Good. This is already solved for y. So I would probably choose the third, although this seems simpler because there's no square for time. I would probably choose the third because this is going to be y equals. Is that logical? But both work. It's okay. I'd rather you think it through now, today, than when you get to the test, right? So we're going to say y max equals y0 plus v0t, and this is t max now we're going to use, plus 1/2 a t max squared. Notice I'm using a subscript of max for y and t because I'm talking about the maximum height when the time it takes to get to the maximum height is utilized. So we know that it starts at the ground, so y0 is 0. Drop that off. But unfortunately, that's the only thing that drops off. So now it's a plug and chug. Okay, no rearrangement at all. Let's get y max. Okay, it's a plug and chug here. We're going to plug in. We got 25 times 2.55 plus 1/2 negative 9.81 times 2.55 squared. We're going to get a height of approximately 31.85 meters. Around 31.85 meters. Our answer is positive because the object is above the ground. The ground is considered 0 in this problem, so it must be a positive answer. It is logical that it's positive. Does everybody agree with that? Does that make sense? Okay, it is logical that the answer is positive. Now, if I look at this problem, let's get to part C actually before I get into those statements. Part C says, what will its velocity be when it returns to ground level? When it returns to ground level. So what part of the problem are we looking at now when it returns to ground level?
Could you just use the part from when it goes from max height to the ground?
Very good. So let's take a look. I'm going to kind of slide over, I think. Yeah, I can do this, right? Okay. And I'm going to put part C up here. Oh, no, it moved. Give me 1 sec. Sorry. Okay. I'm going to put part C up here. And part C says, again, from max height, falling down now. Oops, let me make that dotted so we know it's falling downward. Okay, earlier it was going upward. So I like Morrow's idea because now we know the max height it's going to start at. And we know that it's being dropped technically, right? Dropped, it stops at the top, it's like it's being dropped. So this becomes now a free fall problem for the second half of the problem. So I could, again, this is ground level right here. This is the ground. What we can do for these problems is we could say, well, it's got a starting height now of 31.85. It's got an initial velocity now of 0 because it's being dropped. And it still has acceleration of negative 9.81 meters per second squared. So this is our new problem for part C. And again, I need you guys to start to think about, and it's easy for you to do it nowadays because you have cameras that can do these like time things, but take a time shot or whatever, the time lapse of this going up. At the top, it stops, and now it's a new problem. It's a free fall, and that's what we're seeing here. From a given height, with no initial velocity, to the ground, under the influence of gravity only, in the negative direction. What formula would I utilize if I want to figure out the velocity, right? The velocity when it returns to the ground, when it hits the ground. What formula am I going to use? Go ahead.
The second one.
Why the second one? Go ahead.
Because there's no time.
Good. The second one does not involve time, and it looks like right now we don't have time. Okay, so I would definitely utilize the second one. Again, some of you might be thinking already ahead, like, oh, time, I know something about it. Hold off for a moment, because we're going to get to that, I promise. But we don't know that yet. Once we prove it in this class, we'll use that idea going forward. So right now we know nothing about the time on the way down, which is why we're going to use this formula. So to get v, again, I'm going to take the plus or minus the square root of that whole thing. Okay, v0. v0 is 0, though, so that drops off, actually, right? We don't need v0 anymore. So this just becomes plus or minus the square root of 2a delta y, which will give us a negative number. Why is it negative? For sure. Why is it negative on the way down? For sure. Because it's falling downward. What does my number turn out to be? Approximately. To the nearest integer. To the nearest integer, what number do I get? Square root of 2 times 9.81 times 31.85? I normally tell you the answer, but I want you to do it. I'm asking for it now because it's going to be kind of interesting to see. Come on, I'm waiting for the light bulb to kick in and the aha moment.
Would the delta y be negative?
Y minus y0, right? It would be 0 minus 31.85. So yes, it would be negative. You're going to get error, non-real answer, if you don't make your y negative, yep, because it's delta, it's changing from top to bottom. What do we get as a number when we take the square root? No one's got it? Really? Nick, what do you got?
Negative 25.
Yeah. What was the VI? What was the VO to start the problem?
25.
So what does this problem exhibit? One word. One word. Symmetry. There it is. The answer is absolutely, it's around this, by the way, because we rounded 31.85, so it might be like 24.99 or something again. This is negative 9.81. This delta y is 0 minus 31.85. It's a negative times a negative, which is a positive under a radical. You can't have a square root of a negative, it's imaginary. So if you got a non-real answer, you made a mistake plugging this in as positive by accident. This would be 0 minus 31.85. Yeah?
So the amount of time that you were talking about, is that the time would be the same on both sides?
Very good. And Valentina had her hand up earlier because she was going to say, let's just use the time. Because of symmetry, the time up equals the time down. So look at part D. How long will it take for the rocket to return from max height to ground level? The answer is just 2.55. And if you don't believe me, you can check. Okay, you can check. Part D. I would use this. V equals V0 plus AT. I would say my final velocity is negative 25. My initial velocity is 0. This is negative 9.81. And times time. And look, solve this. 25 over 9.81 is going to get you right back to 2.55 seconds. So symmetry is exhibited not just in velocity, but also in time in this problem. Very good because of symmetry. Yes.
Is this like the same for all like throwing up things?
So this, let's write this down with a big asterisk. This is only true when you start and end at the same position. So if I launch something up to a window, or if I throw something from a cliff down to a canyon, this theory doesn't make sense anymore. It's not going to work. It's only for symmetric problems, therefore it's got to go up and back down with the same delta y up as down. Okay? It's got to exhibit symmetry in not only the time, but also in the geometry. The last one I want to get to today is, when will the rocket reach a height of 26 meters? And I want to make sure we get to this one because the next example is easy, number 3, if we can do this last one. So when is it going to reach 26 meters? Real quick. You're going to use this equation right here. Okay? And I want to just point something out. When you plug everything in, the only variable left unknown is going to be t. But it's a quadratic. It's a quadratic. How many answers does a quadratic give you? So, you're going to get 2 answers. The answers are going to be, just so you know, the answer is going to be 1.5 seconds and 3.6 seconds. Which is right? Which is right?
1.5.
Both. One's on the way up. It reaches 26 meters. It goes up to 31.85. And then what happens? What happens?
It reaches 26 again.
It comes down on the way down and reaches 26 twice. Okay? So, again, I want you to finish example number 3 over the weekend, please. You have homework. Your due date for the homework is already on Moodle. It's on the next slide right here.